on closed thin-walled tubes. All right, so we already looked at torsion of open thin-walled sections last time. And so now we're going to consider torsion for closed thin-walled tubes. I will probably be posting a homework assignment by the end of the day today, so keep an eye out for that. It would have been due next Friday, but since next Friday is a holiday, I'll probably make it due on Thursday next week. So, yeah, I'll take a look. But I think I already considered the following Monday, and that didn't make sense with the schedule. So, but I'll take another look at that. So I think the due date's going to be next Thursday. All right. Any questions for me? Okay. Good deal. Don't forget about the homework due this Friday. Circular beam stresses, Castigliano's method, and strain energy stuff. So we're going to go back to our ubiquitous kidney bean shape, except this time we're going to assume that it is a thin tube, right, or thin-walled tube. And it's considered thin-walled generally if the thickness is much less than the circumference. We are also going to assume that the thickness varies along the circumference. So this will allow us to develop a general solution for these types of problems. And then it will simplify if we have a section that has a constant thickness. But if it varies, we'll still be able to solve for it. So consider this element where x is along the longitudinal axis about which the torque is applied. And we're going to zoom in on this finite area, A, B, C, D, right? So take a chunk out of that, and we have one thickness on one side and a different thickness on the other side, right, as we go around the circumference. So if we sum forces in the x direction, let's see, so I'll say on A, B, C, D, let's sum forces in that x direction. So we'd have negative shear stress on the side labeled 1, right, associated with thickness 1, over the area which it acts, which is T1 times dx, plus, on the other side, the shear stress tau 2 times thickness d2 and dx. All right, so this leads us to tau 1 T1 is equal to tau 2 T2. So we can conclude then that the product of shear stress and thickness at any given point is constant along the circumference. All right, and this conclusion may be familiar to you from mechanics of materials. So this product is also known as the shear flow. Which is, in this class, I use the lowercase f to denote shear flow. You might have seen it as a lowercase q in the past. So we have these relationships that we can work with to relate shear flow to shear stress and the thickness of the material. So our next goal is to relate this shear flow. Since it is constant along the circumference, we're going to take advantage of that and use that to relate to the applied torque. And then from there, we can relate the applied torque to shear stress and or thickness. All right, so let's consider an arbitrary point within the cross section of this kidney bean shape. So P is some arbitrary point. It's not necessarily the center of twist. It's also not necessarily the centroid. If we consider a finite length along the circumference, ds, right, then the shear flow acting on that finite length, right, would be F. And the resultant force that acts on that finite length due to the applied torque would be the F times ds. We also know that torque is equal to a moment, right? So torque will be for just this portion of ds, right? The torque on that portion will be equal to the resultant force on that portion ds times the moment arm to this arbitrary point. So dt is equal to r times f ds. And RDS, it's not immediately obvious maybe, but it's going to be equal to 2 times the shaded area shown in the image. All right, so that shaded area just encompasses the finite length ds on one end and then narrows to a point P that we are referencing. All right, so to verify that, that's going to be 2 times 1/2 base, which is ds, times height, which is r, which is rds. All right, so now we have an equation for torque related to shear flow, right? We used just an arbitrary length ds to develop that. We integrate that equation, we can get an expression for torque about the entire circumference. So we have torque is equal to, we can bring shear flow out front of the integral since it's constant. And then within the integral, we have rds. And so I'm going to write that this is equal to 2 times shear flow times capital A sub m. And I will define that term right now. So AM represents the solid area that is enclosed by the median center line of the circumference of the cross section. So the M stands for median. So if you imagine within this element, right, identifying the median point at any given location and then figuring out what that line is, everything within that line, all right, so that circumference will enclose an area. That entire area is the value of AM. So even though you don't have material in that entire area, you still count for that space in AM. So that's why I'm saying it's the solid area. Maybe it makes more sense to say the entire or the whole area.
Total area.
Total area.
Yeah, I feel like solid implies the solid material.
Yeah, that is fair. that includes the hollow space. And half of the material thickness. All right, so combining our equations, we have shear flow is equal to tau times thickness, which is equal to torque over 2am. So this is where we can obtain a simplified version if the thickness is constant. So say if, and that's a big if, lowercase t is constant, then the shear stress is equal to torque over 2 lowercase t am. And it's important to note that this is an approximation, right? So it will predict values that are lower than the exact values. And the accuracy will improve as the ratio of r over t, the lowercase t thickness, is increased. So I'll jot that down. All right, so to solve problems, it's of interest to know the rate of twist theta, right? Because remember, similar to previous lectures with the open thin-walled sections, how we said that rate of twist is going to be the same for every segment and the entire cross-section, right? It's not going to change. That's the same is going to hold true for these sections. So if we can relate the rate of twist to everything, then that's going to help us solve our problems. So to find the rate of twist here, we're going to come from the energy argument. So for a closed loop cross-section, with a shaft length of capital L, if we apply a twist by a torque, capital T, that gradually increases from 0 to the final torque, all right, so under those circumstances, we know that the angle of twist, phi, is going to increase from 0 when the torque is 0 to the final angle phi when the torque is at its final value of capital T. And that final angle phi is going to be equal to the twist rate theta times the entire length L. So the work done by the torque is going to be equal to 1/2 times the torque times the angle through which it causes deformation. So that's your external energy. As far as internal energy goes, we're going to think about strain energy. So we'll start with the strain energy density. And we've been using the lowercase u with an underscore to represent that value. So that's equal to 1/2 times the shear stress times the shear strain, or making our constitutive relationship substitution, 1/2 times tau squared over capital G. And then our strain energy, capital U, is equal to the integral of the strain energy density over the volume. And since the cross-section is a closed loop, we can write this as the integral over a closed loop, which if you may or may not have seen that before in one of your calc classes or something, but we just superimpose a circle over the integral symbol to denote that. And inside the integral, we have 1 over 2g times tau squared times the thickness times the length times ds. All right, so the last 3 terms that I wrote down represent the volume. So then for energy balance, all right, we set the external work equal to the internal work. So we have torque times theta L divided by 2 is equal to the integral over the closed loop of 1 over 2g times tau squared T L ds. So we can solve for theta. So theta is equal to shear flow divided by 2GAM. All right, so that's making some substitutions in the equation there. Times the integral over the closed loop of ds over dt. Or we can write theta is equal to torque over 4GAM squared times the integral over a closed loop of ds over dt. Now that integral over the closed loop, right, of course that's taken around the center line of the circumference, and that would simplify significantly if the thickness is constant, right? I'll just note that here. Any questions so far? No? Okay. All right, so we'll continue with a few more things and then go to an example. All right, so if we have a straight line segment, if the thickness is constant for a given segment, or for each given segment, I should say, and by that, I mean, I'm saying along its segment length to sort of clarify that this doesn't mean all segments have to have the same thickness, but a given segment should have the same thickness along its own length. Then we would have the integral evaluation of ds over dt can be expressed as simply a summation of the length of a given segment divided by its thickness. So, and of course would be the number of segments. Now, if the cross-section is a closed tube with some open-ended fins, which is, we'll look at an example with one of those. Then you basically have a combination of thin closed tube and open thin-walled sections to think about. So I'll show you what that means in a second. We still have the criteria that all segments will twist through the same angle of twist phi and the same rate of twist theta. All right, and remember that's always going to be true. So we have our torque will be equal to the torque in the closed portion of the cross-section plus the summation of the torques in the open-ended fins. And so we can write that as g times theta, and then inside brackets, we have 4am squared over the integral over the closed loop portion, ds dt. So that first term is the closed loop torque, and then the second term will provide the open-ended fin portion of the torque. So that is coming from the last lecture, right? Remember that was going to be equal to 1/3 times t cubed over, or what is it, t cubed L over 3 was the torque, and then times g theta. So t cubed over 3 g theta is the torque. So if we know the total torque for a given cross-section, we can find the twist rate theta, right, from the above equation, and then we can find the individual components of that torque, right? So what portion of it is in the closed section and what portion is in the open-ended fins. And we can also go ahead and find the shear stresses, etc. All right, so let's apply this to an example. I'll give it a second for when you finish writing. All right, awesome. So here we have a closed loop portion, and then the open-ended fin is this one segment right here. We have all straight line segments, and each individual segment has a constant thickness along its length. We do have some varying thicknesses between segments, so we'll just have to keep a note of that when we do our calcs. The applied torque is given as 6,000 Newton millimeters, and the material property for shear is 80 gigapascals. So we're looking to find the rate of twist, the torque, and shear stress in each segment. All right, so we're asked to ignore stress concentrations. Stress concentrations would occur at corners and intersections. So we're just going to ignore that and keep it simple for ourselves. All right, so first, let's consider the closed portion. All right, in order to do that, we need to calculate the area within the median line, so that AM value. And that median line is just going to be only for that closed portion, right? I won't sketch the whole thing. But that's going to be, since the dimensions that are given are center to center dimensions, we can just use those directly. So 18.5 times 19.5 gives us that enclosed portion. And that's 360.8 square millimeters. So the integral over the closed loop of ds over dt, since we have straight line segments, we can use that simplified calc on the previous page. It's just the summation of the segment's length divided by its thickness. So we have, starting at the top and going around counterclockwise, 18.5 over 2, and then plus 19.5 over 2, plus 18.5 over 1, plus 19.5 over 1. That amounts to 57.0. Oh, and that's actually unitless. So we're going to find the twist rate, knowing that it is constant. So torque with a capital T is equal to G times theta. And then inside the brackets, I'm just pulling the same equation from the previous page. 4am squared over the integral about a closed loop, ds over dt, plus 1/3 times the summation of the length times thickness cubed for each element. So now plugging in numbers, we know everything we need to calculate theta, right? We're going to solve for theta. So the torque was given as 6,000 Newton meters, or Newton millimeters is what it was given as. And for G, we have 80 gigapascals, so that's 80 times 10 to the 9th newtons per meter squared. I'm going to go ahead and convert that to newtons per millimeter squared. So that would be times 10 to the minus 6. And then we have theta, and then inside our square brackets, 4 times 360 squared over, oh wait, I forgot the 0.8, 360.8 squared, divided by 57 for the integral evaluation. So that's the closed loop portion, and then from the open-ended fin, we just have one segment, so it's simply 1/3 of the length, which is 15.5, and the thickness, which is 2. And that thickness gets cubed. All right, so just gut check, make sure we have consistent units within that bracket. All right, so first term, we have millimeters to the 4th from this right here. That's the only value in that ratio that has units. And from the second term, we also have millimeters to the 4th. Solving for theta, we have 8.18 times 10 to the minus 6. And remember, theta is a rate of twist. So the units that are appropriate would be radians per millimeter. And the length in the denominator represents the length along the longitudinal axis, right? It's a rate of twist along the longitudinal axis about which twisting is occurring.
So does that mean that it twists at a progressively, like, faster rate towards one end?
Yep.
Okay.
That's right, yeah, so the rate of twist is, it's going to be constant for a given cross-section, like for a given location along the length. If you take a cut and you look at a cross-section, theta will be constant for that whole cross-section, right? But if you move another distance along its length, you're going to have a larger twist rate.
So you're saying that if you went like 1 meter down this shape or whatever,
Mm-hmm.
and it twisted by 1 degree, you go down another meter, it might have twisted in that second meter by like 2 degrees.
Exactly, yeah,
Interesting.
yeah.
Cool.
Yeah, so I think it's, if you imagine, all right, something that's fixed at one end, and here's your torque, right? That would cause twisting that direction. So your angle, right, your maximum angle is going to be at the free end, right? At the fixed end, you're not going to have any angle of twist, right? So it's kind of along those lines. You're going to have like, if you imagine how, I did a terrible job of drawing that line straight, but if you drew a line along its length and then twisted it, that line would do something like that, right? So at this location, that distance is basically your rate of twist, or that, not that distance, but the angle.
Okay.
Let's see, it's confusing because the angle is constant, right? So that distance is related to your rate of twist, which is tied to how far this point has moved, right, with respect to the center of twist. So I'm doing a terrible job of explaining that. I apologize.
Sorry.
Is it a linear, it's a linear line then, right?
It would be.
Okay.
Yeah, that line would be, but theta is not, like, this is not theta. Theta is more tied to the cross section. So
Yeah.
you're at this location, right, you're gonna have this point, maybe moves here. Right, so this is your theta. Over here, maybe that point is way over here, right? So that's a bigger theta, if you're looking at the cross-section view, right?
But it's a larger radial distance. That rotate.
Yes, exactly.
Yeah. Can you do that for your plane?
Yeah, so
Not
this
happening.
angle here, right, this angle is phi, right, which is that right? Phi is theta times L. I think that's correct.
Trying to find the example here.
All right, so now that we know theta, the twist rate, we can find the torque in each segment. So for the closed portion, we have theta is equal to torque in that section divided by 4g and am squared times integral over the closed loop of ds over dt. And here we know everything except for the torque, so we simply solve, plug in values. So that's going to be 4 times g, which is, after converting in terms of millimeters instead of meters, that's going to be 80 times 10 cubed. And then we have 360.8 squared for am squared, and then theta is 8.18 times 10 to the minus 6. And then in the denominator, we have that integral evaluation, which is 57. So this comes out to be 5,978 Newton millimeters. All right, so then to find the torque in the fin, all right, you can simply, since we know the total torque, we can just subtract. So that difference is 22 Newton millimeters. So as you might have intuitively expected, that open-ended fin is hardly doing anything to resist this torque, right? The majority of that resistance is coming from the closed loop portion. For stresses, if we first consider the closed loop portion, we have our shear flow relationship is equal to shear stress times thickness, which is equal to torque over 2am. So we can calc that as 5,978 divided by 2 and 360.8, which is 8.28 newtons per millimeter. So where will the maximum shear stress in the tube occur, the closed tube portion? I'm looking for more specifically, like which segments will it occur in?
The thinner ones, right?
Yeah, it'll be in the thinner segments, right? Yeah. So maximum shear stress will be shear flow divided by the minimum thickness. So wherever your thickness is minimum, that's where you'll have the maximum shear stress. In this case, that's just going to be 8.28 newtons per millimeter squared, which is the same as a megapascal. And that's going to be in the 1 millimeter thick sections. For the shear stress in the fin, we use our calculation from the previous lecture for open thin-walled sections. So the shear stress is equal to torque in that segment times the thickness of that segment divided by J star of that segment. All right, so we got 22 for the torque, 2 for the thickness, and then the J star, remember that is 1/3 times the length times the thickness cubed. So that gives us 1.06 newtons per millimeter squared. So it's also interesting to note that, right, the difference in the ratio between the torque that the fin takes compared to the tube, right, that's a much smaller percentage of the torque. But if you compare the shear stresses, right, it's still a decent amount of shear stress in the fin. So, yeah. So basically, open-ended fins do not perform well in torsion and should probably be avoided if you can help it. But sometimes you can't, so you have to know how to assess it. So on the next page, which I think is the last page of this set of notes, you have a handout with a few different types of cross sections. There's a mixture of closed thin-walled, open thin-walled, and solid. And it just has a nice reference for the J star values. And I included, even though we didn't really talk about circular sections because we were focusing on non-circular sections, these are included in here for comparison's sake, right? And also you might need to refer to it for homework. But I wanted to point out that the solution for circular sections, whether they're solid or closed tube, it's exact solution, all right? So these methods are approximate if it's a non-circular shape, but if it's circular, then it gives you the exact solution. It's just that sometimes it's more efficient to use the regular equations for a circle in those cases, okay? Any questions? Okay. Let's see.